This is my 9th talk in my video lecture series on fundamentals of physics. In this particular talk, we will discuss measurement, length as an example. We have earlier learned that predictions and implication of theoretical analysis of any real natural system must be checked with whether they are in agreement with the experiments or not, or at least to the level of precision or resolution available on the particular day. Thus, measurement has a crucial role in establishing the link between theory and experiments. In physical theories, we define a set of physical quantities to describe natural phenomena, and most of these quantities are measurable directly or indirectly with measuring instruments and tools. To just understand the importance of measurement and certain aspects of measurement, in this talk I am using quantities with dimension of length as an example. It will not cover all aspects one should understand to carry out measurement in a scientific experiment. Thus, better understanding of the instruments involved, principle of their working, and the protocol of measurement would be required to carry out an experiment and measure something. The protocol of measurement is very important. These are essential but not included in this talk. It will be taken up whenever essentially required in a typical case under consideration. There are several physical quantities having dimensions of length. For example, distance and displacement, the diameter of a cylinder, or the diameter of a sphere, the length of a cylinder, or dimensions of any three-dimensional objects which are used in describing its shape, and these quantities have dimensions of length and therefore are very important for us in this particular talk. We have binocular vision, or what is called stereo vision, which gives us the sense of three-dimensional worlds. It is interesting to note that Homo sapiens have evolved as a biological species over 3.8 billion years since the first cell emerged after 750 million years of formation of Earth. Homo sapien, as you know, belongs to a subgroup of primates of the group called mammals. One of the common ancestor of primates is shown in the picture. It is known as tree shoe, and a fossil 125 million year old of 5-inch length was discovered in 2002. The tree shoe was not having any binocular vision. It could dodge carnivorous dinosaurs because it was small in size in that particular period, and it could survive the extinction in which dinosaurs become extinct. And we have evolved from the tree shoe to the present Homo sapien form. But in between, the first critical step which our ancestor species took was moving into the trees, and it was a small step but a required critical evolution because life on tree was different. It involved jumping from one branch to another branch and avoid nasty falls in between. It is believed that this led to the evolution of binocular vision, grasping hand, and also stimulated brain size and development of brain in the evolutionary process. We as a Homo sapiens have several positive advantages, and we also have necessary intelligence making us capable of measurement and pursuit of science. That is to say, we were gifted by the nature through evolution to have a sense of three-dimensional world and understanding of events. But later, through development of scientific thoughts, now we have acquired capacity of making measurements through advanced tools and measurements ranging from fraction of nanometer to billions of light years. Human eye is a sense organ that reacts to light, the part of electromagnetic spectrum, and give us vision. Once the light reaches the retina, it is picked up by millions of photoreceptors or light sensitive cells called cones and rods. These cones and rods convert the light waves into information your brain can process, like color, shape, and the motion. We have three color receptors cone in our eye, and dog and cats have only two, and that is why they can't see as many colors as we can see. However, they have wider field of vision and can see better at night. But we are not at the top of the color vision chain. The mantis shrimp, a biological species, has 16 color receptors, enabling 10 times more color than a human being, and probably sees many more colors than any other animal on the planet. But the stereo vision allows our brains to determine the depth and distance. It gives the sense of three-dimensionality of vision. It involves that both eyes must point accurately enough that the object of regard falls on corresponding points on the two retinas to stimulate stereo vision. Otherwise, double vision might occur. In day-to-day life, we make estimates of size and distance based on our vision. So, human eye is like an optical instrument measuring dimensions of length. 80% of everything we learn is through our sight. The vision is also angular, and when things are closer to you, they take up more of your field of view, and so they seem bigger. When they are farther away, they take up less of your field of view and so seem smaller. The angular limit of resolution of human eye is 1 minute, and so at near least distance of distinct vision, which is 25 centimeter, two dots which have a separation of 0.1 millimeter would be resolved by human eye. But two dots which have a separation of 0.1 millimeter will not be resolved if the two dots are located at 25 meter distance from eye. So that is an interesting aspect of our angular vision. And farther is any building, higher is the limit of resolution, and therefore if you look at a distant building, maybe you will not be able to count the number of windows or pillars in the building. Common measurement of less than 1 millimeter and up to 1 millimeter is done by using ruler scales. Common ruler scales are just over 150 millimeter or 300 meter with least count of 1 millimeter. So for better measurement, we require tools like Vernier Caliper and screw gauge, and instruments like Theodolite, microscope, telescope, or bigger setups which we will discuss toward end, the LIGO observatory. Length of a one-dimensional object is defined by distance between the two ends. To measure the length of an object, place the 0 hash mark of the ruler exactly along one end of the object. Align the object you are measuring along the edge of the ruler as shown here. So you have to align, and then you can record the second hand reading and read therefore or measure therefore the length of the object. So if you move the object along the rulers, the coordinates of end will change, but the measured value of length obtained by taking difference of coordinate will not change. So length is invariant and it doesn't depend upon where you place the object on the ruler scale. The length of an object is absolute in Galilean theory of relativity. However, later we will consider special theory of relativity in which the length contraction is a phenomenon and which tells you that length of an object is not same in all frame of reference. In a moving frame of reference, length would appear to be smaller than the length in the rest frame, and that's why the name the length contraction. But in our series of lecture, in the current topics which we are considering, we are limiting ourselves to Galilean theory of relativity. Measurement of length or distance using scale is an example of measurement of quantity. In rectilinear motion of a particle has zero size, but it is located in one-dimensional space at a point A at some instant, and at a later instant it may be located at a different point B, and we have considered this in defining kinematic quantities in our previous talks. So when it makes a journey from A to B and that along a straight line without changing the direction, then the length of the distance traversed in one dimension can be expressed in same manner as length of object by using meter as unit and by using coordinates of initial and final position to determine the distance traversed. But if the direction is changing in between, and then you have to measure the distance traversed with same direction in each segment, and then you will have to add all those distances which are measured in a particular direction. As many number of times the direction changes, so more number of terms you would have to take into account to measure the distance traversed by a particle in one-dimensional motion. Remember that length of one-dimensional object is an intrinsic property, but distance traversed is not an intrinsic property. Distance traversed or displacement is an extrinsic property of the particle, and from which we have defined other set of extrinsic properties like instantaneous velocity and instantaneous acceleration, etc. So to measure a physical quantity, we need tools and instruments. Now we have a sense of size of different three-dimensional objects, but our measurement based on our senses can be helpful in qualitative understanding of which object is bigger and which object is smaller. But scientific measurement require a better degree of precision. So we have to develop and make tools and instruments for measurement whatever be the physical quantities. However, in this talk I will confine myself for the tools and instruments which can be used for the measurement of the dimension of length. In Euclidean geometry, length is measured along straight lines unless otherwise specified. Later we will say that the distance traversed along a trajectory, and that may involve interpretation of how to calculate distance along the length of a curve in 2 dimension or 3 dimension. But length measurement means what? The length measurement gives you a value of length in the units which we have chosen, the SI unit meter, and which is the standard comparison unit. Length of any one-dimensional object, as explained earlier, can be measured by placing it in alignment with the ruler scale, and with the ruler scale you can determine, for example, here the length is 2.2 centimeter as measured, and this ruler scale and common ruler scales have 1 millimeter as the list count, and the numbers, the hash marks which are given are for centimeter only, and between 1 and 2 centimeters we have 10 subdivision, each subdivision corresponding to therefore 1 millimeter, and so by counting the number of subdivisions you can arrive at this figure of 2.2 centimeter. But when we make measurement of, say, the length of this particular object as 2.2 centimeter, what we can actually mean to say is that the length is between 2.1 centimeter and 2.3 centimeter. Certain level of uncertainty is always there in the process of measurement. So if you don't look carefully, maybe it can turn up as 2.1 or 2.3. So whenever we specify physical quantities after measurement, we also assume that the last digit which is used with significant figures, which we will discuss later, this will be uncertain digit. So when I say the length of this screw is 2.2 centimeter, the 2 which is after the decimal point is an uncertain digit, and this is just an example. And the list count of any instrument is very important, and the list count of a measuring tool or instrument is the smallest and accurate value in the measured quantity that can be resolved on the instrument's scale. The list count is related to the precision of an instrument. An instrument that can measure small changes in a value relative to another instrument has a smaller list count and is therefore considered as more precise instruments. So in course of development of new instruments, we would always try to make the instruments which are more and more precise. There is another issue of measurement which we will discuss in next talk, and that is called accuracy of the measurement. But we design the instruments in such a manner that we achieve the precision, best precision possible in that particular design, with that particular design. But it is a constant ongoing process in science, and therefore we always aim at improving our instruments to achieve better and better precision. So that's about the list count. For measurement of length, we can make use of many tools like the ruler scale which you have, and maybe in your school you have done this experiment, or most of the schools have in physics laboratory the tools like Vernier calipers and micrometer screw gauge. All these tools are important in the course of measurement, but we can compare, because the ruler scale, the list count is just 1 millimeter. There are generally 10 line subdivisions, as I have explained earlier, in 1 centimeter, and so the list count of a common ruler scale, whether 150 millimeter scale or 300 millimeter scale or even the meter scales, the best list count which you get generally is 1 millimeter. However, you may have some scales which has half millimeter marks also. But Vernier caliper is a tool and which is used because in the scientific measurement, because it can provide me a better precision, and it has a list count of 0.1 to 0.01 millimeter. And the micrometer screw gauge have far better the list count, in the sense that the list count is smaller and it is 0.005 millimeter for micrometer screw gauge common. And we also have Vernier micrometer screw gauge, and which can also better the micrometer screw gauge and can have resolution up to 0.001 millimeter. So that's what we have noted. Now I would say something about this instrument, this tool, which is called Vernier caliper. The Vernier caliper is a precision instrument that measures internal dimensions, outside dimensions and depth. For measuring the internal dimension, inside jaws will be used. For measuring the external dimension or outside dimension, the outside jaws will be used. And for measuring depth, the depth of an object or hole would be used. The Vernier caliper incorporates a main scale and a vernier scale. So in most of the Vernier caliper you also have imperial scale, but I am ignoring imperial scale which gives you the reading in inches, and I am considering only the main scale which is in centimeter and the markings are up to say millimeter. So in this particular case there are 10 subdivisions between say 7 and 8, and which tells you that the list count of the main scale is 1 millimeter like your common ruler. But the vernier scale has certain number of divisions on it, and in this particular case the number of the scale marks on the vernier scale is 20. So there are 20 subdivisions on the vernier scale, and so we define the list count of the Vernier caliper or list count of the vernier scale as the list count of the main scale divided by the number of divisions. And since number of division in this particular example which is shown in the picture is 20, so you have a list count which is 1 by 20 millimeter. Remember, 1 millimeter is the list count of the main scale, 1 by 20 millimeter is the list count of the vernier scale, and which is here. Therefore, this particular Vernier caliper has a list count of 0.05 millimeter, much better than the ruler scale. So is suitable for measuring, for example, the diameter of a cylinder, the outside diameter, the internal diameter, or the sides of the cubes or any objects, for example, the length of that screw which I have shown. So this instrument can be used to make measurement, and here I have shown that the varieties of measurements can be done in this picture. You can measure by using out jaw the length of this screw. You can measure the outside diameter of this particular cylindrical pipe, and also the inside pipe, diameter of the pipe. So for inside the up jaws are used, and for outside the main jaws are used, which I have shown you earlier. And for probing the depth, this depth probe is used, and we can make measurement of depth also using Vernier caliper. But whether you make the measurement of internal dimension or outside dimensions or depth, the same main scale and vernier scale readings you will have to note. And how to read the main scale reading? There is a 0 mark on the vernier scale, and just on the left of that 0 mark the main scale you have to read. So for here, if you read the main scale reading, if it is clearly visible to you, then you will note that the main scale reading is 2.4, which means after the 4 subdivisions are on the left of the 0 mark, and so my main scale reading is 2.4. Then to read the vernier scale reading, because in this instrument you will have to add both the readings to get the measurement value. So to read the vernier scale reading, you have to find there are marks on the vernier scale and marks on the main scale, and look for where the line up in perfectly line up. The vernier scale mark is in perfect line up with a mark on the main scale. In this particular example, I have shown that here it is in perfect line. You would find that at some point here the marks on the main scale and the vernier scales are shown here. So this is the main scale, this is the vernier scale, and you find here what is happening. The vernier scale mark is slightly on right and that size is decreasing, and at this particular point we find that the marks are in alignment perfect, and therefore this is after 15th subdivision. So we take the vernier scale reading as 15 into 0.005 millimeter, which was the list count determined by us. So the vernier scale reading is 0.075 centimeter and the main scale reading is 2.4 centimeter, and therefore the total reading is 2.475 centimeter. In this manner you can make use of it. In most of the vernier calipers, it is appropriately because the caliper is designed with a particular list count. So here you can directly read also the Vernier scale reading that it is after 7, so the Vernier scale reading is 0.07, and if the 1 mark after the 7 and therefore 0.075, and if it was the number 16th subdivision was in alignment, then you would have only 0.080. Since only 15th subdivision is in perfect alignment which we are observing, so we say that in this particular case the reading of the Vernier scale is 0.075 centimeter and it is not 0.080 centimeter. It would be 0.080 centimeter if the 16th, here you find that the 16th subdivision is slightly on the left hand side to the main scale marking, and therefore a careful reading is very much essentially required in determining the measurement or value. So the measured value in this particular case turns out to be 2.475 centimeter. If you have placed the object in between, and if this is the answer, it is the diameter or whatever the length you are measuring of the object, and whether you use inside jaws or outside jaw or you use the depth probe, remember the measurement is done by the same scale and it will not change. And because this instrument is perfectly designed, so whichever kind of the measurement you want, internal dimension, outside dimension and depth, the same main scale and Vernier scale will work. So it's an interesting experiment which you should perform. Nowadays it has become much easier because we have available digital caliper in which the reading is shown digitally in the digital display, and you can directly record, and there is no need to calculate the reading from the main scale and the Vernier scale reading. So these kinds of digital caliper are available in present time. Now I come to the next important tool which we have to measure, and that tool is called the screw gauge. A screw gauge is shown here. It's a mechanical tool which facilitates measuring diameter or radius of a wire, of a thin wire, or thickness of a thin wire, or thickness of a thin metal sheet or glass slab or things like that with better accuracy than we can have in Vernier caliper. It has several components which are visible and have been marked here. A stud and spindle, and the object or the wire will be placed in between, and this ratchet is used to rotate and to place the wire perfectly for the reading in between the stud and spindle, so that they can the stud and spindle both are touching the exterior side of the wire. In this particular instrument you have a scale given on the sleeve which is called the main scale or sometimes called spindle scale, and there is another scale which is given on this thimble and which is sometimes called thimble scale or the circular scale or rotatory scale. Different books may use different name, but there is a circular scale and there is a main scale, and this ratchet is used to move the spindle and press the spindle, move the spindle in this direction. So whenever we make measurement, the list count of both the scales would be important. Just like Vernier caliper, in this case also we have to record two readings, one that of the main scale and the other of the circular or rotatory scale. On the main scale, for example, in this particular screw gauge which is shown in the picture, what is the list count for the main scale? It is 0.5 millimeter, better than the earlier Vernier calipers, because in the earlier Vernier calipers example we were having the main scale list count as 1 millimeter. Here we have the main scale list count as 0.5 millimeter, and so the main scale list count is 0.5 millimeter, but on thimble, on the circular scale, there are 50 divisions, and therefore we divide the main scale list count by the 50 and we get the answer of the list count of the micrometer screw gauge. And so we find that this screw gauge has a a list count of 0.5 divided by 50 millimeter. So it's better than that, and so the list count is 0.01 millimeter. Sometimes the list count in some literature you will find that the list count of the main scale is also called pitch. What is pitch? So pitch sometimes is defined as that if you make a full rotation of ratchet, or which means a full rotation of the thimble, so from one zero to another, next appearance of the zero with the baseline, there is a baseline here on the main scale, and so in a full rotation the advancement of spindle in a direction is equal to the pitch, and so the word pitch is also used for the main scale list count in context of the screw gauge. So pitch here is 0.5 millimeter, but on circular scale or thimble scale we have 50 division, so the list count as pointed out earlier is 0.01 millimeter. Now you can make reading of the main scale, the visible divisions. In this particular case, if you look at carefully, then you will find that after 0 mark, 3 more subdivisions are visible on the main scale, and therefore the main scale reading is 1.5 millimeter. And now look at this baseline. Here is 15 and the 14th subdivision on the regular circular scale is just below this baseline of the main scale. So we say 14 is the circular scale reading, and it would have to be multiplied by the list count. So 14 into 0.01, and that means it is equivalent to 0.14 millimeter. So when I add the two readings, the readings of the main scale as well as the reading of the circular scale, I get that whatever I am measuring in this setup, or this distance between stud and spindle, the gap between the stud and spindle at present is equal to 1.5 plus 0.14, which means 1.64 millimeter. And since it has better resolution, it is preferred. And then the vernier calipers, when we have to measure some small sizes like the diameter of a wire or thickness of a glass slab, etc. But we can further improve these instruments, and we can combine the approach of both the screw gauge and vernier caliper and make this instrument called vernier micrometer screw gauge. Vernier micrometer screw gauge is a tool which has 3 scales instead of 2. Therefore now the main scale, which is shown here, the rotatory scale and the vernier scale. But the difference in this case is that you can make measurement just like a screw gauge for the main scale, and here you find that the main scale list count is 0.5 and the reading of the main scale is after 5 one subdivision is visible, so 5.5. And on the vernier scale, this is the baseline. So the baseline, the 28th subdivision is just below the baseline, so 28 is, and since the list count in this case is also 0.01, so you get the reading from the rotatory scale or circular scale 0.28. But now you have to look for which line on the vernier scale is in perfect lineup with the line on circular scale. No main scale in this case, but a line of vernier scale should be in perfect lineup with the line on the circular scale. And here we find that this line, third line, is in perfect lineup, and therefore I have written that the resolution of this instrument is 0.001 millimeter, because we will have to divide the list count of the rotatory scale by the number of divisions on the vernier scale. Since number of division on the vernier scale is 10 in this particular case, and the list count of the rotatory scale is 0.01 millimeter, so this vernier micrometer screw gauge will have a list count of 0.001 millimeter. And the example shown here, we have measured the value and it turns out to be 5.783 millimeter. You can perform these experiments by visiting the site www.olabs.edu.in. It's a collaborative site of a program supported by the Ministry of Electronics and Information Technology, Government of India, Amrita Vishnu Vidyapeetham and CDE. And there you will get an opportunity by using online lab concept to perform the experiments using Vernier Caliper, screw gauge and other measuring tools. Since I have not demonstrated anything and I have not used any animation or movie in my video integration of such measurement. However, there are plenty of videos are available on YouTube also, which can train you in how to make measurement using Vernier Caliper and the screw gauge. You should explore, in my opinion, this particular site www.allabs.edu.in, and the access is free to my knowledge. Now, to make measurement of the quantities which are even smaller than 0.001 millimeter, then we have to invent new instruments, and a microscope is an instrument which is used to examine objects that are too small to be seen by human naked eye. And so for those instruments we have designed the optical microscope long back. And here a picture of the optical microscope is shown here, and this is the picture of an optical microscope which is commonly used in biology laboratories in school and colleges. And through this microscope you can see the objects which are called microorganisms in biology, the organisms which have size of the order of few microns only. And here it is shown bacteria are also such microorganisms, and here it is shown the E. coli bacteria picture has been taken by using an optical microscope, and this particular length scale shown here is equivalent to 1 micron. So by using optical microscope you can achieve a magnification as up to the order of say 10,000 times, and therefore you can look the things which we cannot look by our naked eye. So in my earlier part of the presentation I have emphasized that we have been gifted by the nature that we have binocular or stereo vision, and we can see and we can interpret the distance and depth. But we have moved ahead with the scientific approach and created instruments, and these instruments help us in looking at dimensions which are otherwise not accessible as per our biological design. So there are several types of microscopes available and which have been developed by scientists for making measurements. So we have the microscope called transmission electron microscope, and scanning electron microscopes have higher resolution even than transmission electron microscope. The TEM has higher resolution than the optical microscope, and that is why TEM we would prefer over optical microscope if required for a scientific measurement. But the same, and which is the scanning electron microscope, is a better resolution than TEM. And the difference between SEM and TEM is that SEM creates an image by detecting reflected or knocked off electrons as being shown here in the picture, and that is the way to create the image. While in case of TEM it is the transmission and transmitted electrons through the material of sample which helps us in creation of image. Now we have improved the resolution further, and by using the approach which is called scanning probe microscopy. So we have we have SPMs which are much better resolution than the scanning electron microscope. One of the SPM, there are different types of SPM. One of the type is shown here is atomic force microscopy. The other is scanning tunneling microscopy, and the third example of SPM shown here. There are many examples more than that also, but third example which is shown here is scanning near field optical spectroscopy. And why I should go for a better instrument, higher resolution instrument? because in science to verify the theory we need better precision or accurate measurements in the experiments, and that's why we have been paying emphasis. So in this way, since 1830 when we started having optical microscope for exploration of scientific studies, and the graph has been changing, and nowadays we have the resolution which is less than even 1 nanometer available in laboratory instruments like aberration corrected transmission electron microscope can have much better resolution of less than 1 nanometer. So we can look at the nanometer scale or nanoscale. It is the scale at which the even manipulations of atoms can be done, and which has led to the development of new technology which we call the nanotechnology. So nanotechnology has become feasible because we have improved capacity to make measurement at the nanoscales, and now we can understand the nanostructures, nanocomposite, the nanomaterials, and these new smart materials, and can understand the physics associated with them. Right now we are not at the stage where I can deliberate upon those ideas, but whenever we will take up the nanotechnology, definitely these discussions would again come up about the microscopes which are used for making measurements at nano or sub-nano scale. So remember that the resolution of the measuring tool or instrument is very important issue, and we started with the human eye which had a resolution of 0.1 millimeter, then Vernier Caliper which has the human eye can resolve 0.1 millimeter, but the common ruler scale have divisions up to 1 millimeter only, and then we made the Vernier Caliper which can have from 0.1 millimeter to 0.01 millimeter list count, and then the vernier screw gauge or the micrometer screw gauge can further improve. The best resolution for optical microscope is about 0.2 micron, and a typical electron microscope, as I have pointed out, can have a resolution of even 200 picometer. So the best transmission scanning transmission electron microscope may have resolution of 50 picometer. So that is how the technology has helped us in making better and better instruments which can be used in measurement of dimension of size or length which are much smaller than what we see in day-to-day life, and so all those measurements are possible. But again we have to look at the entire range. So some of the things we can measure by using microscope, and some measurements can be made by vernier caliper or screw gauge or by using ruler scale. But for measuring long distances you need the tools like measuring tape or measuring wheel. This measuring tape and measuring wheels, you can measure the size of a room or a building or an apartment, and for drawing the maps of such places you need measuring tape, and the measuring wheel when we lay the cable is also useful. Now we have much better facilities available, and we also have a measure long distance. We can use the laser measure, and the laser measure gives us more accurate result of the measurement, and you can just point out the laser measure to a wall and can know the distance of the wall from the site from where you are standing and throwing the laser light on the wall. And if the angle can be precisely measured, then we can also obtain the height by using geometrical method shown here in the picture. That height of this tower can be measured by using geometrical methods, and there are many other geometrical methods of determining length by using geometry. And here this angle theta if we measure, and if we measure the base, then we know that height upon base is tangent theta, and so height can be measured or obtained in this particular example by measuring base and measuring this angle. And angle measurement is also therefore connected with the measurement of length in physics, and that's why we have this particular instrument also, a theodolite. This instrument is used by geographers and for surveying land and for measuring distances by taking even looking at the different objects in a real life scenario, and this particular object can measure angles in both the vertical and horizontal plane. So theodolite, maybe you are having in your school in geography lab or wherever the geography or land surveying is taught, definitely they would be having theodolite. Theodolite can be used to measure angles, and with one known distance as shown in this picture, with the known distance and by measuring angles, all other unknown distances can be calculated by using this theodolite, and that's why it is very useful in infrastructure construction, in land surveying, in meteorology, or even in rocket launching. So if you get an opportunity, you should also, but it's a sophisticated instrument and you would have to learn. However, in modern time, we have theodolites available with a digital display, which makes the reading, noting down the reading quite easy for us. But still, there is a protocol for measuring angles associated with this particular instrument, and that protocol you will have to understand first, and you have to get a practical training of how to make measurement using theodolite. Otherwise, the measurements would involve personal error, and your measurements will not be of worth. So that is why an experimental course in physics is very important. But even if the distances, like we see the height of a tower or a big multi-storied building or the land surveying, there are also the distances which are far greater than this, and we have to design instruments also for measuring those distances. And before that, I would also give you an information that there are nowadays available several mobile apps which you can download from the Play Store or Apple Store, and these mobile apps can be used to make measurement. And but you have to check whether the particular app is giving what kind of accuracy or resolution in the measurement. And again, an app should be properly used. Unfortunately, now we have mobile apps for measurements which are supported by augmented reality. So which you can see here, this is the augmented reality creation, and which makes the process of measurement quite simply and enjoyable to you. In my opinion, you must try at least one mobile app. Now some of the mobile apps are also having some sort of artificial intelligence, and so can pick and read from the image and can provide you the different measurements very easily. Not many apps are available. The two here are shown just for the purpose of example. But to measure the distances much greater than the distances in a city or town, we have to invent new instrument. And telescope was such a major breakthrough. A telescope is again an optical instrument which uses optical lenses and curved mirrors or combination of them to observe distant objects of various devices used to observe distant object by either by emission, absorption or reflection of electromagnetic radiations are classified as telescopes. Remember that the earliest existing record of telescope, we don't know about who has actually invented, but the earliest available record of the telescope is that it was patented in 1608 by the Netherlands government. And then the great scientist Galileo came to know about it, and he made his own version of telescope in 1609. And often many people give credit of invention of telescope to the Galileo, but it is on record that prior to the Galileo, the telescope was invented by an unknown inventor, and it was patented by a particular company in Netherlands for the use. But remember, the telescope has led to a revolution in astronomical observation, and that is why Galileo is also known as father of astronomy. He is also called father of scientific method or father of modern science because of his contribution. and he started how to make use of experiments, and he conceptualized and did several experiments, and which we will come to know later on in our discussions. But this was a major breakthrough, the invention of Galileo. But don't think that the astronomical data was not available before Galileo. The great scientist Nicolaus Copernicus, the Tycho Brahe and Kepler are prior to Galileo, and they have collected large astronomical data. And in fact, Tycho Brahe collected a large amount of astronomical data through direct observations with eye and could record them and or for over years, and based on that particular data the Kepler could derive certain laws or could arrive at some certain empirical laws, we will say, which were in agreement with the data which was taken by Tycho Brahe. So the astronomy is older than Galileo, but Galileo is known as father of astronomy because of this invention of telescope helped him in making observations of the distant object, making the study of how far the different objects are by using the optical and other telescopes. Now we have wide-ranging telescopes. All these telescopes are based on electromagnetic wave. But as you know that electromagnetic wave spectrum is very big spectrum, and we can only see a part of the electromagnetic spectrum through our eye, and that is called visible light. And visible light has wavelength in the range of 390 nanometer to 750 nanometer, and you can convert it into frequency, or in terms of energy you can say that the visible light photon has energy in the range 1.7 electron volt to 3.3 electron volt. These figures may vary in different books also, because how to define the visible light, there is no consensus in my understanding, and so the different books got different figure, but I am taking 390 nanometer to 750 nanometer as the visible light, and the wavelength less than 390 nanometer would be called the ultraviolet, and ultraviolet and the wavelengths which are more than 750 nanometer would be called infrared, because you know that the visible spectrum is a spectrum from red to violet, and violet Vibgyor, and the violet has less wavelength and further less is the ultraviolet, and since the red has the highest wavelength and the further high is the infrared radiation. The ultraviolet, visible and infrared radiations are produced in optical transition mainly, and these X-rays and gamma rays have different mode of productions, and similarly the microwave and radio waves have different type or mode of production. We will discuss all these issues whenever we will be taking up electromagnetic waves in this spectrum. But you know that each telescope which you have either work in one of the region or 2 or 3 regions out of these regions, and the greater is the energy of the photon, the better is the resolution, or you can say less is the wavelength of the wavelength used in telescopic measurement, the better is the resolution. So the best resolution we can have is from gamma ray telescope and X-ray telescope, and the poor resolution we have definitely in comparison to gamma ray and X-ray in ultraviolet, visible and infrared telescope. But that doesn't mean that these telescopes are also not important, because these telescopes work by detecting ultraviolet, visible and infrared radiations, and there are numerous sources of these radiations in the visible cosmos, and therefore we have to make use of this particular region or spectrum also. Then we also have now microwave telescopes and radio telescopes, and whenever need will arise for knowing in more detail about any particular telescope, I would again take it up. But telescope is an instrument which is used to make higher measurement, or which means longer distances, or which you can call the astronomical distances. One of the interesting telescope which I wish to show you in this particular slide, the picture is shown, It was launched in April 25th, 1990. The name is the Hubble Telescope. It was designed to examine ultraviolet, visible and infrared light waves. It is solar powered space telescope and it can collect about 40,000 times more light than the human eye, and that is the advantage therefore we have. And it is 13.2 meter long and it weighs 11,110 kilogram. The Hubble Space Telescope, like satellite, is orbiting our Earth, but it is just 547 kilometers or 340 miles above the Earth, and it travels at the speed of, you can say, 8 kilometers every second, not hour, 8 kilometers every second. For hour you will have to multiply this number by 3600, and the orbit is inclined, and many the satellites which you know, the communication satellites, they are in a particular plane, but here the orbit is inclined to 28.5 degrees to the equator, and it completes one orbit in every 97 minutes. This is a fantastic telescope which we have designed and the NASA has put in this space, and which has been used for obtaining large number of images in due course of time. And the farthest galaxy it could observe was about 13.4 billion light years away from us, and the name of the galaxy is GN11 galaxy. But I am showing you picture of one of the interesting galaxy, and that is NGC 2336 galaxy, which has been taken away. However, it is closer to us and this particular galaxy, and you would enjoy that this image is very beautiful image of an object which is 100 million light years away from us. So that makes it clear that why improving telescopes, why designing better and better telescopes is very important, because you can get fantastic pictures and images. Lot of such images are available on the NASA website, and I therefore advise you to have a look at the NASA website and look at the different images of cosmic objects available on NASA website. Another big breakthrough which happened in the last decade, in fact, is that the laser interferometer gravitational wave observatory. The general theory of relativity tells you that there must exist gravitational waves, and the scientists were therefore aiming at looking at or detecting gravitational waves. And to detect the gravitational waves, a big project, collaborative project called Laser Interferometer Gravitational Wave Observatory was established, and under this collaboration you will be happy to know that on 11 February 2006 the collaboration published a paper saying or reporting the detection of gravitational waves. And however, the detection of the gravitational wave actually occurred much earlier, and from a signal which was detected at 0951 UTC on 14 September 2015. This gravitational wave reached the Earth, and the source of the gravitational wave was the merger of two 30 times solar mass black holes merging into each other, and that too not very close to us but about 1.3 billion light years. This may seem to you, and the picture or the data is shown here, taken from the two different laboratories. One is located in Washington and another in Lausanne, and the distance between these two laboratories in United States is about 3002 kilometers. So very interesting observations were made, and we could record this rare event of the merger of two black holes which caused the emission of gravitational wave, and which this particular LIGO could detect it. But it has opened a new prospect for us. The earlier we were having telescopes which were working only on electromagnetic wave spectrum. Now with the detection of gravitational wave, we are planning and thinking of using gravitational wave for telescopic and cosmic measurements in the cosmos, and one day that would be feasible. So a new branch, a new possibility has opened up with this LIGO discovery of gravitational wave or detection of gravitational waves. And it is also a success of general theory of relativity, which predicts existence of such waves in nature. Now, because you can make an understanding about the astronomical long distances, what I am doing, I am defining here certain units of the astronomical which are important at the astronomical scale. Because at the astronomical scales of measurement or cosmological scales of the measurement, the use of meter would not be very convenient. However, we use it because it is the SI unit, but we have also certain practical units which are used in course of measurement of astronomical long distance. One of the major reference is the distance between Sun and Earth, the center of Sun and the center of Earth. It has been defined as one astronomical long distance or one astronomical unit long distance. So one astronomical unit by definition is the distance between center of Sun and center of Earth. And you will be happy to learn that this distance can be measured very precisely in modern times through the instruments. And so we have a many significant figure knowledge of the 1 AU. Now if you have to measure the distance of any star, a distant star or nearby star, then you can use the parallax method. What is the parallax method? That the measurements are made 6 months later. So after 6 months, the Earth would be at a different position and in its own orbit around the Sun, and it can be called diametrical opposite. So two measurements are made, one measurement at some date, and then after 6 months another measurement is made, and by using that measurement data you can determine this particular angle which this distance is subtending here at this nearby star. This 1 AU, the length is subtending at this particular point of the location of the distant star. If 1 AU is subtending an angle of 1 arc second, then that is defined as 1 parsec. So that is very clearly shown in this picture, that 1 AU subtending an angle of 1 arc second. Remember, you know the degree, and 1 degree has 60 minutes and 1 minute has 60 seconds, so arc second. So 1 arc second is a very small unit of angle, and if you compare it with the radian, then it is 0.00029088 radian. So very small unit of angle. But with sophistication of our instruments, we can make such cosmic measurements. So 1 AU, if subtend 1 arc second angle on a distant point, then that particular point is said to be 1 parsec away, and we write PC as a symbol of parsec and AU as the symbol of the astronomical unit. Another astronomical unit which is commonly used in astronomical and cosmological discussions is the light year. 1 light year is the distance which light travels in 1 year time, very big time. So 1 year, as I have earlier pointed out, is nearly 3.15 into 10 raised to power 7 second, and the speed of light was also given to you, and it is nearly approximately 3 into 10 raised to power 8 meter per second. So you can understand 1 light year is a very big unit of length, and 1 parsec is nearly equal to 3.26156 light year, and you can also express 1 parsec in terms of meter, and here we have to use petameter. 1 parsec is equal to nearly 30.85677 petameter, and I have used many significant figures because these quantities are known better accuracy, with better accuracy nowadays. And however, approximately you can say that 1 parsec is nearly 31 petameter, or which means to say nearly 3.1 into 10 raised to power 16 meter. So it's a very long distance which we have knowledge of. Some of such long distances I have given here as an example. The Proxima Centauri, the nearest known star to Earth, other than the sun is about 1.3 parsecs away, and if you convert that into light year, it is 4.24 light year away, and is the nearest known star to Earth. And so you know that from that nearest known star, light will take 4.24 years to reach us. So if you are looking at that particular star, then it is based on the light emitted by that star and reaching your eye or telescope. But that particular light must have been emitted before 4.24 year than the time when you are observing. So in that manner also the light year tells you to put proper perspective of astronomical and cosmic measurement. Remember, the center of the Milky Way is 8 kiloparsecs away. So 26,000 light year away we are from the center of the Milky Way. But the Milky Way, the dimension, the size or diameter is of the roughly of the order of 34 kiloparsec or 110,000 light year, or you can say 110,000 light years. It's the distance. The Andromeda galaxy is about 780 kiloparsecs or 2.5 million light year away from the Earth. And in my earlier presentation, I have already talked about the particle horizon, the size of the observable universe as per Big Bang theory of cosmology, because in the Newtonian universe the size is infinite, and that is the radius of the observable universe is about 14 gigaparsec or 46 billion light year. So very big numbers are there. So in this particular talk we could see that we can make measurement from the below nanometer, so picometer scale, few picometer, few tens of picometers, to the 46 billion light years, the understanding of the observable universe dimensions in terms of the experiments as well as in theory. We have to cover a long range. So length is just one fundamental quantity, physical quantity, and which is the base quantity defined in International System of Quantities. And we have noticed that lot, because it has such a long range, that we have to design the different instruments and tools for measuring length. And this is just an example. Every time I would define a physical quantity, it would not be possible for me to tell you about how that particular physical quantity is measured, what are the measuring instruments and tools available to us, how scientific experiment is done for measurement of that particular quantity. We will not be able to discuss it in that manner, because my emphasis is to learn theoretical framework, to communicate theoretical frameworks to you. But experiments are very, very important, and at the same time they are very, very challenging too, because we would define a large set of physical quantities in our due course of discussion, and each physical quantity may have a long range of values, and we have to have instruments and measurement techniques and tools for measuring those physical quantities. And that is what makes the scientific studies or the study of physics or the physics experiments and theory and the development of the technology very, very interesting. So with this I conclude the today's talk, where I have described length as an example of measurement, and I have not given the entire detail which should be given in actually for carrying out the measurement, but I have highlighted certain aspects of the measurement, and some aspects are still pending with us, and therefore in the next talk we will discuss about error in measurement, so we can understand what we mean by accuracy, we can understand what we mean by precision, and how whether every precise measurement is accurate measurement or not. We have to understand that. And when we make a measurement, how we should specify the measured value. So how many significant figures are involved in a particular measurement, and how the quantity should be specified by using significant figures. So the notion of significant figures, what we mean by that. And towards the end, I would also have some saying on dimensional analysis in the next talk. And in the next to next talk, I would be first introducing vectors in 2 and 3 dimensions so that we have necessary mathematical tools to understand kinematics in 2 dimensions and then kinematics in 3 dimensions. I hope that you are liking my video lecture. You can click the like button. You can subscribe my YouTube channel A for Science by clicking the subscribe button, and if you click the bell icon with subscription, then you would also get notification from the YouTube whenever the new lectures would be uploaded. I hope you are enjoying this series. Thank you for being with me in this series of presentation.